Exponential functions, basic growth and decay. We're going to look at some more word problems today using exponential functions. This time, we're not given the formulas. We need to use our knowledge of exponential models to figure out what to do. Let's read the first problem. A town has a population of 14,000 and grows at 3% every year. What will be the population after 14 years to the nearest whole number? So our most basic exponential function looks like this. Y equals AB to the x, where A is our y-intercept or starting point, and B is our growth factor. To figure out this growth factor, we're going to need to use some information from the problem. It's growing, so it's keeping at least 100% of the original, and it's adding an additional 3%. 100% plus 3%, that's 103%, which we could write as 1.03. Let's try that in here. If I've got my y, what I'm trying to find out, I don't need to type that into the calculator here, but I do need that a, the initial amount, 14,000. 14000. The b, the growth factor, well, we said that was 100% plus 3%, or 1.03. And our exponent, our input, is the number of years that will pass. So we raise this all to 14. And we get 21,176.256148. Another way that we could look at this is break it down a little bit further. We could use our exponential growth model. Y equals A, parentheses, 1 plus R over 100, all raised to the x. What's similar here is that we still have a function trying to find that output y. We're still using A to represent our initial amount, and we still exponentiate the x. The difference here is that where we had a simple b, where we had to do a little bit of mental math in the first example, we're replacing that b by explicitly writing out the mental math that we did. We added 1, or 100%, plus the rate that we saw, 3, divided by 100 to get it out of percent form and into decimal form. Let's use this formula and see if we get the same output. My A is the same, 14000, but now let's do this growth factor in parentheses. Parentheses, 1 plus the rate as written, 3, divided by 100, close parentheses, all of that to the 14 years. And we get the same output. So these are two different ways that we could approach the same problem. First way, we're doing a little bit more mental math. Second way, we get to show the steps all written down. Regardless, I'm going to write down my answer. Since we're using people as the units, it's asking us to give whole number answers. So let's give that, let me move myself out of the way. 21176. I'm getting rid of 0.2. That's not big enough to scale things up. So 21,176. Submit. Great. Let's see if we can do a problem that uses decay. An element with mass 210 grams decays by 8.3% per minute. How much of the element is remaining after 15 minutes to the nearest tenth of a gram? Let's do it. So we could use our first model, y equals AB to the x. Our A represents our starting amount, 210, and our B is the growth factor. Well, we're going to have less than 100%, so it's 100% minus 8.3%. We could do some mental math in our heads to get 0.917 and then raise that to the x, the time, in this case 15 minutes. Let's also look at how we could use a decay model. Decay model looks almost exactly like the growth model, except it's 1 minus the rate over 100. Close, raise it to the x. Again, my initial starting point, is 210, multiplied by 1 minus 8.3 over 100. All of that raised to the 15th. We got the same number. Phew, I did the mental math correctly up here. The result is still 57.2478696182. 57.2478696182. Excellent. Let's record that answer, being careful to round appropriately. 5, 7, they want the nearest tenth, so that's 1 decimal space. What are we cutting off after the 2? Well, it's just a 4. 4 is not big enough to round up, so we leave the 2 as it is. Submit our answer, and we're good to go. Let me know if you have any questions, and good luck.